Thank you, Dom.
Feigelson again.
Well, a few weeks ago, I made a mistake. I told Roberto Palladini that I would give a general talk in the morning and a specific talk called Statistical Approaches to Exoplanetary Science in the afternoon. And then I sat down to write this talk and realized that it would probably take about a week to cover this, and I'm not competent to cover most of it. So I really limited the whole thing. And really, I'm going to talk about time series analysis for radial velocity and transit studies. And even then, I'm going to talk about time domain methods and then frequency domain methods. Every textbook in time series is divided in these two parts. I'm then going to talk about non-parametric and parametric methods in each one of these, except I'm really not going to cover this fourth one very much. And even this is incomplete. For instance, wavelet methods are missing here, and they're sort of a fascinating combination of sort of time and frequency type transform, and there's many other methods I'm not covering either. In other words, I can't even cover a subtopic of what I propose to talk about, okay? So with that preface, let's now start. I'm going to start with non-parametric time domain methods and concentrate on non-parametric regression. So I went to the web and I pulled off 2 years of ground-based radial velocity measurements of an HD 3651 star. And as you can see, it's a sparse data set and it's unevenly sampled, which means it's nasty. So you read the textbooks on time series analysis, and there's dozens and dozens of them. There's not a single textbook, except for one dissertation in econometrics, okay? Not a single textbook that covers unevenly spaced data of this type. So therefore, it's rather troublesome, okay, that we have to face these things. Okay, so let's now see, by the way, she reports a period of 62 days and an eccentricity of 63% for this planet. Okay. So let me talk to you about non-parametric time domain methods, particularly something called local regression. There's others. There's simpler ones, something called kernel density estimation, convolving a Gaussian through it, for example, is a very common kernel estimator. But let me mention this method, which locally calculates typically a quadratic polynomial through the data, going point by point and choosing a window, fitting a local parabola and patching them together in a smooth fashion and going through the data in this way. And really what this is an interpolator. It's a smoother, okay? But when you do this, I just want you to think of what you have to decide. You have to decide, for instance, how to weight the points. Let's say this is the point we're going to choose. As you go further and further away, do you choose a uniform box, which is not a good idea, by the way. It gives a jumpy estimator, or a Gaussian, which is good. They recommend most the Ipanichnikov kernel, which I'm sure you've all heard of, the Ipanichnikov kernel. It's an inverted parabola. It ends up mathematically, it's the best kernel of all. Okay, so you got to choose your kernel function. Most importantly, you have to choose how wide is it? How smooth is your smoother going to be? Right? If you smooth too much, you'll just be a straight line. Smooth too little, it just jumps around. And so there's something called the Bias-Variance Trade-Off. And there's procedures for estimating this trade-off. There's books on this, okay? I recommend the one by Larry Wasserman called All of Non-Parametrics. He discusses it very nicely at the graduate student level. Usually done through cross-validation techniques, which is sort of like a bootstrap. But why don't we just say you can either choose a constant bandwidth, which is what's done here, or an adaptive one that actually makes a narrower kernel when there's a lot of data and a broader kernel when there's fewer data points. You can use likelihood methods for estimating this as well, and it goes on. Then you have to decide locally, am I going to do a constant, a linear, a quadratic, or a cubic fit? Then you have to decide what is my fitting criterion. Am I going to use least squares or maximum likelihood? Sometimes those are the same and sometimes not. And then what about getting these confidence bands? We definitely like the idea not only of smoothing, but getting the errors on the smoother, and the errors should change so that when we have very sparse data or very scattered data that we get a broad confidence interval, and when we have denser data that has smaller variance that we get tighter confidence bands. So we have all these things that we want. That's usually done either if you make a Gaussian assumption with the local standard deviation inside the window, or more commonly it's done through the bootstrap, which allows non-Gaussian scatter. So 1, 2, 3, 4, 5 decisions to make in order to make a curve like this. Okay, now one of these methods, there's a whole bunch. There's spline regression. There's a LOESS, L-O-E-S-S. That's the oldest one, dates back to the 1970s. There's various local regressions, and this one's using a code called LockFit by Clive Loader. And another one is called Gaussian processes regression. And it's one of these local polynomial regressors that assumes that the errors are normally distributed, which is a reasonably good assumption. In fact, what I like about this, a lot of regressions, a lot of things that require, by theorem, they require normally, that normally means Gaussian, distributed residuals, so that you can test it after you've done the regression, plot the residuals, and do a test for normality. So it's very easy to say after the fact whether you're allowed to have done it, and if you're not allowed to do it, then throw it away. Okay, so it's a perfectly reasonable thing to do because you can check it using, for instance, the Anderson-Darling test. So GP regression was actually first invented in 2 dimensions by geologists in the 1960s. A mining engineer named Krieg invented it, and it became known as Krieging. And they make maps from irregularly spaced measurements of cores underneath the ground, maps of the layers of granite or shale, and particularly where the oil is. They were doing oil exploration. So all exploration of oil depends on GP regression, but they call it Krieging. And they get, it's a 2D version of this, they get a map, the best estimator map, and then they get a variance map called a variogram of the other map. So this has been used for 60 years. So the astronomers sort of discovered GP regression, particularly the cosmologists. In the last few years, it's now quite popular. And there's nothing wrong with it. It's a good method. But it does require normally distributed residuals. Okay. In this case, I read Deborah Fisher's paper and folded this with 62-day period. And here we are in days. And you can see, and then I did another one of these. And you can see it's fairly evenly populated. It doesn't look quite Gaussian. This particular model I used didn't require Gaussian residuals. And here is her astrophysical fit, okay, using an elliptical orbit of a single planet for this. This is a larger data set. This is a subset, just for our little illustration here in the workshop. So this is just an example of how local regression, it's non-parametric. You made no assumption about the overall shapes. You didn't know or assume that it was an elliptical orbit. Can be very effective in almost all branches of astronomy when you don't know what's going on in terms of formulas and you just want to sort of smooth the data in an intelligent fashion. Sir? Yeah, Xavier.
Question. So you said that there is 2 points here in this case that are not, like, that don't follow a Gaussian distribution.
Yeah, well,
but
perhaps.
in this case, like, you don't take error bars. So perhaps those 2 points have
Yeah.
very bad signal to noise,
Yeah.
and therefore they are unnatural.
Yeah.
But most of the parametric models don't take into account error bars.
Okay, so I'm not going to read this. This is just, it will be on the web if you want. This is the data, and this is my R script, okay? And this, it's extremely simple, and this is the thing, it's one line. First, one line, install packages, lock fit, local fit. And so one line on the fly, you install any of the 9,000 packages, and then you just run it in one line. And here it is being run in one line. Then this is plotting and running it again. Modulo, that's a modulo symbol there, and plotting it again. And this is just bringing the data in. And if you want a more detailed tutorial, here's a website where I give a longer tutorial on these local regressions, again with R. So this particular one, Xavier, I like LockFit because this particular one allows heteroscedastic measurement error weighting. So it does allow it. Most of them don't, but this one does. It allows censoring upper limits, okay, and as well as detections. There was something else, and it allows non-Gaussian unity. There's several options for the confidence bands, and one of them is local bootstrap that allows non-Gaussian unity. So this particular one, there's about 5 or 10 of these codes in R, is very flexible and is admirable in this respect. I may not have done it all correctly here, but in general. Okay. Okay. Local regression, ladies and gentlemen. Gaussian. How many of you do GP regression of some sort? GP. A few, not too many. I thought it might be more. Okay. Okay. This is like a really picky thing. I don't mean to be nasty. Don't call it Gaussian processes, because that's a very large field of a field called stochastic processes. Call it Gaussian processes regression, and that's what this is. It's a regression tool. It's not study of Gaussian processes. Okay. That's petty. That's just language. Okay. Okay, so that was non-parametric time domain. Just things like smoothing the light curve to take a look at it. And I didn't go into it. There's an entire lecture on how to try to estimate things like not only the bandwidth by cross-validation, but an adaptive bandwidth. And that actually, there's no consensus, there's no like theorems on how to do an adaptive bandwidth, but there are, what do we just say, favored procedures. One by Abramson in 1982 that's very simple, and astronomers aren't doing it, and it does have a theorem behind it for certain limited circumstances. And so it's not easy. Astronomers probably do more adaptive smoothing than almost anybody else, and so we should pay attention to that. It's a tricky step. Okay, another non-parametric procedure is, another scientific procedure, goal is to find periods in light curves. And certainly in exoplanets, we definitely love periodicities. I mean, this is the essence of it. If it's not a periodic phenomenon, then it's not an orbiting planet, or we can't find it. So we're constantly doing this in exoplanetary research. So there are non-parametric periodograms that date back 40 years. So you're mostly young. Do you know about Stellingwerf's phase dispersion minimization? How many people know Stellingwerf, know about it? Well, that's not good, guys. Okay, your grandmothers and grandfather astronomers were doing this, okay? I mean, this is like a standard thing where you just fold it with different trial periods, fold the light curve with different periods, and then you bin it into maybe 10 bins, and you just compare the intra-bin, the sum of the intra-bin variances with the inter-bin variances. And when the data closely follow the broad shape, then there's a dip in the PDM periodogram, and you see a signal, and it's a period. The advantage of this particular non-parametric periodogram is that it treats well non-sinusoidal shapes, like eclipses, like short-duty cycle eclipses, and other things like the elliptical orbits that where most of the signal is concentrated in a small fraction. Because a Fourier analysis requires a sinusoid to be most efficient. It's looking for sine waves, and PDM is looking for anything. The problem with it is that it has an arbitrary guess. You don't know how many bins to divide it into. And then it uses Gaussian statistics, just chi-squares and stuff. It's not necessarily bad. In fact, Stellingwerf's method is actually rather good. It's been used by, I would say, 1,000 papers in astronomy have used it, roughly. Mostly in something called variable star research. Okay, that was all before they discovered planets. Okay, they had binary stars and rotating stars. Okay. So there's another version of it called the minimum string length by Dvoretsky. It's less popular. It only has a couple hundred citations. It's another non-parametric measure. It's closely related to the Durbin-Watson roughness statistic. I won't go into it. But it's very similar. It's just unbinned. But there are parametric approaches when you think you understand the formula, the mathematical family that your periodic behavior comes from. And the mathematical family for transits is called the box. And the procedure that's become very popular for good reason is the box least squares, BLS. How many of you know BLS? You either do it or you know it. Ah, everyone. Okay. So BLS is great. It's wonderful. It's a parametric, non-Fourier, time domain periodicity search. Okay, so it sort of has a purpose, a category. Okay, and it's really nice. Okay. So, of course, the main problem with everything, this is for all of them, not methods, the problem astronomically is this darn star is not constant. When the planet's going around and causing the dips or causing the radial velocity variations, the star is doing its own thing, often due to magnetic activity of some sort. So we already, of course, heard about this from various presenters today, and we'll hear about it all week, I'm sure. So if you have long-term trends, like, I don't know, 11-year cycles or something like this, you can use GP regression, Gaussian. Oh, it might even work on shorter periods if you have enough data. Okay, but it's not optimized. Gaussian GP local regressions are not optimized for something called stochastic autoregressive processes. So what's a stochastic autoregressive process? Stochastic means that it's random, so it's aperiodic. And autoregressive means that the current value is related to the previous values. Okay, so let me give you an example, or a couple examples. Ready? The wind in the trees, the sound. Okay. The bubbling of a brook. The sound of a waterfall. A Mozart symphony. The human voice. It's all over. There's autoregressive time series like all over the physical and natural and the human world. It's amazing how often it occurs. It occurs in electronics, so it's there in engineering signal processing as well. Okay, so it's used incredibly often. So it ends up that 50 years ago, engineers and mathematicians, statisticians, developed analytical models that are stochastic. They're actually parametric models, but they don't look like polynomials. They have a different look. And if you want to go see one, see my poster out there. Okay, you go outside, it's just on the left. And you can see some of the formulas that go into it. I'm not going to show you the formulas here. But let me sort of give you a sense of it's sort of like a family of models. Okay, so the simple one is called AR, autoregressive, where the current value, you may know this from the physicist random walk, right? Random walk, like this. It's random in direction, but it's constant step size and a square root of time, you know. And so my current value depends on my past value. So that's AR1, okay? Then there's MA1, where the current value of how big a step is related to, autoregressively, how big a step I chose last time. So the sizes of the steps change. The I integrated is actually a sort of different. It's a differencing operation. The simplest version of the I is a differencing operation where I transform my time series that's going like that, and where I take each value and replace it by the difference between the current value and the previous value. I just take away yesterday's value. And it actually flattens an amazing amount of what's called non-stationary behaviors. In other words, trends, non-stationary trends, arbitrary shapes get taken away that way. The F, if it's a fractional integrated model, it's a more complicated procedure, and it's equivalent, mathematically equivalent, to 1 over f to the alpha, red noise, which the physicists and the astronomers like, okay, which is a long memory noise. They call it long memory processes, or both of us, they and we call it red noise. And the coefficient value is alpha. It's also called the Hurst parameter, which is the economist's name for it. And then sometimes they add an H on it called heteroscedasticity, a word I may have used before. And that means that the variance, the current value, the current first derivative of the value, the second derivative of the value depends on past variances. This is called volatility. So here are two of the more advanced models that come out of the ARMA, A-R-M-A, ARMA family. Garch. So Garch is used by economists to make money, okay, on the stock market. It's very effective for volatile, autocorrelated, choppy stock markets. generalized autoregressive conditional heteroscedastic models, okay? Okay, that's why you're not making money on the stock market, because the other guys are using it. Actually, your guy may be using it for all I know. I don't know. Okay. Okay. We're using our FEMA models. Autoregressive moving average fractional integrated models. So these are formulas, and sometimes you can't write it all down directly, but it's analytic. So this is very powerful because it deals with non-stationarity, that's the I, short memory, that's the ARMA, and long memory, that's the that's the F processes. It does everything. So we've been applying it to Kepler stars, the Kepler light curves, okay? And I'm going to show you a couple examples. And there's a poster out there with more of the math. My student is named Gabriel Caceres, and he and I have been doing it with the advice of some Chilean statisticians. Now, before you get too excited about how wonderful this is, I got some bad news for you. For us. It's bad news for us. Mathematically, it only works on evenly spaced time series. So you radio velocity people, unless you go back every night, forget it. Okay, the photometrists, most of the ground-based, forget it. Kepler was the best. But we have 15% missing data in the Kepler, okay? And we're still doing fine. And our FEMA hasn't failed yet. In fact, we have an NSF grant specifically to see how well these methods can work on ground-based data. In other words, as you increasingly make the sampling lousy, when does the method begin to fail? So I don't know that. Nobody knows that because no economist bothers to find that out. And they're the only ones who work on this. Okay, here you are. Here's a typical four-year light curve. This is 4 years of data. Every 29 minutes, there's a data point. Okay? Here, this is the original flux. It's actually something called the PDC flux if you're a professional. It means it's been corrected for a lot of instrumental work. There are some gaps. Okay? Here is an FEMA model. We kept it down to less than 10 parameters. So it's anywhere between a 2 and 10-dimensional thing. We don't even care what the parameters are. The economists don't care about the parameters on the stock market. They just want to make money. I don't care what the parameters are because I can't interpret it in terms of stellar activity, although maybe someday we'll try. We'll maybe try to classify them or something. But you can see it sort of looks pretty good. I mean, just, you see what I mean? It sort of looks like it's capturing a lot of this signal. That's only, I don't know, I should have checked this particular one. Let's just say it's roughly 7 parameters. 4 years of data with all the weird behaviors are only 7 parameters. It's an analytical model. It's a deterministic model. So this is the separation between them. Now the amplitude here was about 50, and the amplitude here is about 10. But more importantly, the FEMA model takes away the autocorrelation. Almost all the time we get almost white residuals. White meaning white noise instead of autocorrelated noise. And we use the autocorrelation function, the ACF, to do that. So now we're going to then look for planets here. Now Gabrielle's major concern, which was a big one, was we did such a good job modeling the star that we modeled the planet, of course. And everyone has to worry about that. And the Kepler team, John Jenkins' pipeline, worried a lot about this. They do this through wavelets, but they worry a lot about getting rid of the planets, and they fiddled around with their wavelets and this and that to try not to do that. So we didn't fiddle at all, but we're lucky. This is a maximum likelihood solution using Akeyiki information criterion model selection. This is the statistical language. There's a well-established formal procedure for doing these fits. And we're lucky that it treats all the data homoscedastically so that if only 2% of the data are involved in the transit, it doesn't get modeled very well. So we're left with this signal, except now the differencing operation turned a box into an ingress and an egress spike. So we have a double spike. So Gabriel Caceres, my student, developed a new periodogram, a new filter, equivalent to BLS. It's not a box, it's a double spike, but it's very similar. So there's the residuals again. It's just reproduced from the previous page. And here's the periodogram. I chose one that looks nice. Look, we found a peak, okay, at 11.191409 days. And here is the folded light curve. There it is, but ingress, egress. Okay? So we don't see the box. The box is gone. There's too many steps. We can't go back and still find the box. We find the double peak. So we did this, and you'll have to look at the poster. And we've recovered roughly 85% of the KOIs from DR24. It's specialized jargon for Kepler people. It means that we reproduced most of the same results as the Kepler team did for periodic behaviors. We're not telling the difference at this point between eclipsing binaries. We're not doing astronomical false positives. We're just doing periodicity search. And we get almost the same results. But we don't confirm their lower amplitude long periods, and we're going to find some new ones as well. So now we're doing the DR25 sample, and we haven't published yet. We're cautious. We're worried that our method wasn't going to work, but it looks really good. It looks really nice. So this is an example of a topic in parametric time domain time series analysis, where astronomers just happen not to know anything because they don't read textbooks. It's in every textbook. ARIMA models are in every textbook. They're used, thousands of times a day by other scholars, and astronomers didn't know it. And in this particular case, oh, by the way, it not only worked on this star, but it works on an incredible variety of different shapes. All the same code. It's just one line of R. We don't do anything. We don't fiddle with the models. It just does it all and automatically finds the best model. They do really, really well on almost everything except for the Cepheid variables and a few others. It doesn't do well on periodic stars. Okay, so there's the early results. The black dots show that we confirm most of the models for most of the periods, but the red and green dots are the ones that we don't confirm, which are low signal-to-noise long-period models from DR24. Okay, so this is just an example. Frankly, it's my only personal astrostatistical research project is this project. And it comes from having authored the book and reading about our FEMA models and scratching my head and saying, hey, I wonder if they work on stars. And it really does seem to work. I'm convinced that there's lots of things in the textbooks in statistics that are waiting to be mined and used by astronomers in this fashion. Okay, what about astrophysical models? In other words, not stochastic autoregressive models, but like real models that have ellipticities and masses and TTVs and stuff like this. And of course, this is what most of you do, we do as a community. Here is what a regression is. This is the way a statistician writes down a regression in principle, and I'll read it to you in English. The expectation, or the mean, of the dependent response variable y for a given value of the independent variable or variables, there could be 100 of them, x, is equal to a specified family of functions which depends on x and a vector of parameters theta, which you saw, I think Jesse's showed us theta in another context, plus a random scatter that's usually considered to be a normal distribution with zero homoscedastic normal in most cases. So this is it's a different way of thinking about what we do when we fit models. And here is just a typical radial velocity with a planet C and a planet B in a typical way that we do it. These models are high dimensional because in each planet we have six dimensions. Semi-major axis, eccentricity, inclination, ascending longitude, argument of periodicity, and a true anomaly. And they're nonlinear. And I'd like to go back and make an historical comment and say those of you who fit these models, I think it's great. Here it is, 21st century. But you realize the first person who fit one of these models from unevenly spaced, noisy data, was Johannes Kepler on Mars. No computer, right? He did it by hand. Took him, 3 years or something? And first he did model specification. First he did an oval, and the oval didn't work. He did epicycles, it didn't work, and then he chose an ellipse, and it worked. And that went into his big tomes in the 16th century. And you got to admit that Kepler was a heck of a time series analyst. Okay, he did what we're doing with many fewer tools, and he was the first. Okay, I'd like to comment a little bit, if you want to be honest, criticize a little bit some of the procedures that astronomers sometimes use in this. So here's an example of where they did heteroscedastic weighting, where they weighted by the measurement errors. But you can see that the model, which is this very, very faint sinusoid here, doesn't fit very well the data. There's much more scatter than is allowed by the measurement errors. And so this minimum chi-squared, where you're weighting by the measurement errors, is valid only if the measurement errors are the source of the scatter. As soon as there's some other source of scatter, this weighting is wrong. So this model is wrong. It's published. It's wrong. Okay? After you do a model, please do residual analysis. Do more residual analysis than you're used to doing. Ask the question, what fraction of the original variance is taken into account by the model? In this case, it would be a low fraction, and you'd know the model wasn't very effective. Okay, here are some of the language and multivariate statistics of that variance fraction. Take a look and take the data unweighted and simply plot the cumulative distribution function of the residuals and see whether or not it's consistent with the model. Of the data is consistent with the model. In other words, goodness of fit. An Anderson-Darling test or Kolmogorov-Smirnov test can be done for that, the one sample test. Look for structure in the residuals. Do a local regression, a smoothing of the residuals, so you don't get confused by all the dots and you see the overall curve, including the confidence band. And people aren't doing that. And then just test to see, is there any autocorrelation in the residuals? The Durbin-Watson statistic is a nice, perfectly good AR1 test for AR1. Is it consistent with white noise? If it's not, then run an ARMA model on the residuals and get rid of it and add an ARMA model to your analytic model. In fact, this might help you with your stellar activity problems, meaning the stuff in the residuals that's not due to measurement error is due to something, and if it's autocorrelated, you can probably ARMA it away and be left with a cleaner model. Also, if you did a least squares or a maximum likelihood or a Bayesian, you probably implicitly made an assumption you have normally distributed errors. Well, just take a look at the residuals and test whether they're normally distributed or not. If they're not, and there's a lot of data and they're very asymmetrical, you can actually see the asymmetries, you can run quantile regressions, which are really quite cute, and astronomers are not doing that enough, to study the top 10% and the 50%, the bottom 10%, the behavior of different quantiles of the response variable if it's not Gaussian distributed. And also, and I think Jesse mentioned this, you can ask whether or not certain bad points, or just one we just used the word extreme points or outliers, influence the regression, and something called the Cook's distance plot is designed for that. So all of these are standard methods in regression analysis. They're taught at the undergraduate level in stat classes, and astronomers just don't know it, and they should just learn it and do it. It's very easy. It gives you confidence. If you pass all these tests, then your regression analysis is much more reliable. You feel better. and if you start failing the tests, then you worry, and you have perhaps ways of improving it. Okay, so a few other things that we're not doing. It's sort of redundant. We're not doing goodness of fit tests enough. The model selection using reduced chi-squared equals 1.00 is not a good one because there's no, the criteria for choosing when a model is better or worse, significantly better, is not that good. And we recommend instead the BIC and the AIC, which are related to, under ideal circumstances, to minimum chi-squared. But most statisticians prefer that you work with likelihoods than with chi-squared. When we have a multivariate problem, like 5 or 10 variables, which doesn't always happen in time series of exoplanets, but please do a multivariate regression and not a sequence of bivariate regressions. And worry about these arbitrary transformations, has been mentioned several times already. And the Bayesian inference, if you have no prior information, and you're seeking the mode of the posterior, then you really are doing maximum likelihood estimation. And there is a lot of advantages to MLE. there's a whole machinery associated with maximum likelihood estimation, such as model selection and error analysis, parameter error analysis, which is very easy. It's very simple. So again, I sort of recommend that people do MLE first without a prior, and then if you have prior information, add your priors, and then see how much things change. And you learn a lot from comparing the unweighted and the weighted likelihood analysis. Now, interestingly, a lot of astronomers, as I read the AppJ, say, oh, my method for regression is MCMC. No, that's not your method. Your method is weighted least squares, chi-squared, or is Bayesian inference. MCMC is your tool, is your algorithm for optimizing things or for mapping things or something like this. MCMC can be used for any of the methods. Okay, it's perfectly good for mapping chi-squared surfaces, perfectly good for mapping likelihood surfaces, and it's perfectly good for mapping posterior surfaces. It's great, okay? And if you're just finding the mode, then go ahead and just do any other optimization because it's easier, like simplex or the EM algorithm or steepest descent or really anything. So I think there's too much of an emphasis on the MCMC. Now, you guys, there's some people in the room, when you're doing a 5-planet model from very difficult data sets, you really have to worry about the sort of things that David Kipping talked about. In other words, the actual details of the technologies of your MCMC. My comments here, when I say overuse, is not really addressed to those of you dealing with difficult high-dimensional plot problems like that. It's addressed to a lot of other astronomers who do Bayesian inference in the AppJ when they're basically doing MLE or even just chi-squared, and they're just confused. They don't understand that they're doing something simple. They think they're doing something elegant, and I don't know what to say. It's just a question that Bayesian inference, the first sentence of Wikipedia, the purpose of Bayesian inference is to update your prior knowledge. If you don't have prior knowledge, you're not doing Bayesian inference. I mean, you're not fulfilling the purpose of Bayesian inference. You might do it operationally, but that's not what it's for. So it's really valuable when you have prior information. And you often do. So many of you should be doing Bayesian inference, and I'm really impressed with how well it's being done by some of the exoplanetary community. My complaints are mostly certain stellar and extragalactic astronomers. I mean, I had a colleague who did a beautiful probabilistic calculation, and he put the word Bayesian on the title. And I said, you know, Tim, it's not really Bayesian. You didn't do it. And he said, yes, it is. I said, no, it isn't. And then he wrote an appendix that shows it was Bayesian as well. So, I mean, he's British. The British love Bayesian, okay? So I mean, I don't, it is Bayesian, but it doesn't have to be. You know what I think what it's sometimes like? Okay. When you got to go around the corner to buy a bottle of milk, you get on your bicycle or you walk and you buy a bottle of milk. Well, these people are using a Ferrari or a Maserati to buy the bottle of milk. You know. Okay? So it's not wrong. You did buy your bottle of milk, but you didn't really need your Ferrari to do it. You need a Ferrari to go on a race in Monte Carlo. Okay? Like a 5-planet system. That's a race. That's where you need it. Okay, so I'm running out of time. I'll have to speed up. I'm now moving from time domain to frequency domain. I'm only going to deal with nonparametric methods. So here from Deborah. Is Deborah here? Yeah, was this a Fourier spectrum, or Lomskargel, or something else? It's a Lomskargel. Okay. Okay. So this is a Fourier periodogram. Lomskargel being a generalized Fourier periodogram. And there it is. There's her 62-day period. And notice she has these aliases from the unevenly spaced data. And even worse, she has periodicities in the unevenly spacing because, after all, the 24-hour cycle and the 28-day cycle and then the annual cycle. And we have these really nasty periodicities that are really not very nice and cause these alias problems that are unavoidable unless, well, you can try to avoid them, but if they're often unavoidable. Okay, so let's talk for a few minutes about Fourier analysis. It dates back to the early 19th century. It's also called harmonic analysis and spectral analysis. And I don't know the difference between them. Okay, so spectral analysis reveals nothing about the evolution in time, but rather takes the entire data, assumes whatever process is stationary, the same throughout, and collects all the power at a given frequency and puts it into a single data point. So the power spectral density, also known as the periodogram, is the modulus squared of the Fourier transform of a time series, and here it is back in the 19th century where it was all defined, and it's all based on powerful theorems of mathematics. But it only applies, the theorems only apply if you have a stationary process, your data are equally spaced, you have an infinitely long data set. When was the last time you had an infinitely long data set? Okay? Without edges, okay? And it has to have homoscedastic, that means they're always the same Gaussian noise, white noise. And then if you have a periodic signal, it has to have exactly a shape of a sinusoid, and there can only be one period. That's the theorems underlying the Fourier transform, which means there's almost no astronomical data set that ever satisfies the theorems. So that doesn't mean you can't do it. All it means is you're doing something that you can't get probabilities reliably out of it. That's what it really means, okay? And you get a variety of inconsistencies. It's formally an inconsistent estimator. That's a technical word, not an English word. And you can get biases and aliases and other problems. Now, the Lohm-Scargill periodogram is a generalized Fourier periodogram for unevenly spaced data. Once it's evenly spaced, it becomes the Fourier transform. It's considered to be quite nice. It's very widely used in astronomy. I want you to know that it also has assumptions. It has assumptions of independence that may not apply to your data. There are reports from the physicists that its behavior at high frequencies may be biased as well. It may not be perfect, ladies and gentlemen. There has not been much theoretical work on the Lohm-Scargill periodogram, but it's definitely effective. We know that. We've been doing it all for 30 years, okay? And it's widely used. But you should know if you read any textbook in spectral analysis, written mostly for engineers or for economists, but mostly engineers, okay, they'll all say, oh, well, you have your periodogram from Fourier periodogram. Now you should smooth it. And your smoothing is in the Fourier domain. You just pass a filter through it and smooth it down. And then you taper the original data in the time domain to get rid of the sort of the beating against the edges because you don't have an infinite data set. And that's called tapering. And if you don't know how to taper it, you might do multi-tapering. We're now up to the 1990s. And so what these do is that these things improve the signal to noise of your, if there is a periodic signal, it improves your signal to noise. So astronomers should be smoothing and tapering their Lohm-Scargill periodograms all the time, okay? Because this is what the mathematicians tell you to do. I mean, you lose your statistical characteristics, but you didn't have them anyways because you violated the theorems. So it doesn't matter. What you get is a cleaner periodogram. And if there's a signal, it comes up with bigger signal to noise, or sinusoidal signal. You can also filter. You can do a high-pass filter and a low-pass filter and a Wiener filter and this and that. You can particularly for us with stars, you might want to detrend the data to get rid of the aperiodic long memory processes. The woo stuff, get rid of those that bring up a high amplitude at low frequencies. And those are essentially Arfima models. In fact, you can take out a lot of aperiodic phenomena using Arfima models or simpler versions of it. Or you can just use GP regression or other things as well. So there's all sorts of sort of artistic things that are recommended for Fourier type analysis, for non-periodic frequency domain periodogram analysis. It doesn't matter if you're doing Lohm-Scargill or Fourier or even Stellingwerf or one of the others. All of these problems exist, the issues of the finite data set and the various other constraints, and smoothing and tapering are often effective. In fact, Stellingworth's model, essentially, the binning is a smoothing technique, essentially. So we should read some of the standard textbooks. Here is an example of a standard textbook. Percival and Walden, there's a dozen of these textbooks. This one is particularly written for engineers and physicists and speaks a little bit to us and is sort of nice. Okay, we all want to know, is that faint planetary signal real? We want a false alarm probability, and we do a Lomskargel periodogram. We draw a dashed line, 99%. How did we get that dashed line? Well, we read a paper from the 1980s, Horn and Baliunas typically, and it said, oh, use this exponential, that's the height of the periodogram, and that's the signal to the noise level of the periodogram. And the probability of getting something at that height is proportional to this exponential. Ladies and gentlemen, this formula almost never works. Okay, it's in Percival and Walden's book, Chapter 5. It never works for engineering either in Fourier transforms. It just never applies to real data. I mean, you have to be like the world's most perfect data for this to apply. And here is an example. No one's reading Chris Cohen's paper. Chris Cohen from South Africa has a PhD in statistics and a PhD in astronomy. He's one of the only people. He's a faculty member in both departments. He's unique in the world. People should be reading the papers by Chris Cohen. Monthly notices 20 years ago. I mean, he's brilliant. He's very quiet and he's far away, but he understands his stuff. And this one paper here, very short paper, shows that this is often wrong by orders of magnitude. So don't put FAPs at all in your diagrams. So how do you do it? How do you know it's real? It's hard. I don't have any clear. It's like the rest of harmonic analysis. It's an art more than a science. So this is my own suggestions. First, permute or bootstrap the data after you remove the trends, just to make sure that it's not just noise. Okay. But that still leaves, that gets rid of the autocorrelation. And if autocorrelation is present, which you can test, then you should do an ARMA. You should fit it with an ARMA model and then simulate the ARMA process and put that in with your irregular spacing and do those Lomskargels and see what those periodograms look like. And then you can actually add in the periodogram you think is there to see whether or not the harmonic structure looks like it really does in the real data. And you do all these things and maybe then you can believe it. And the worry is, of course, is that many of the people in our community here are not doing enough of these tests. Maybe they'll do this test, but not the others. And there's no guarantee that you can reach a solid answer because harmonic analysis is just a mess, even for the engineer, even for good data. So my final comments are sort of a repeat of this morning. Astronomers generally are using a smaller, narrower suite of time series procedures than they should. They don't know about ARMA type models. They don't know enough about residual analysis, which is actually elementary, and they don't know enough about spectral analysis, some of the techniques that are used. But it's also true that we are facing a rarely faced problem of irregularly spaced data. And it really behooves us to try to get our instrumentation people and our telescope schedulers to try to put in as close as they can to regular spacing. So for instance, the HAT survey tries to get evenly spaced photometry from the ground. A new one called Minerva is going to try to get radial velocities evenly spaced from the ground. The LSST deep drilling fields hopefully will be largely evenly spaced. Those stars will be far away, not that interesting perhaps. But the traditional way of going up to a big telescope and scratching your head and saying, well, I think I want to look at those 5 stars tonight, that leads to very irregular spacing, which makes almost all time series analysis very difficult. So please, evenly spaced data is valuable for time series analysis. Okay, but we all need powerful time series and regression methods, and they do exist. And that we should be using these more sophisticated methods to improve the power of our science analysis and the reliability of our analysis. But frankly, the kind of problems we have, the 5-planet problem with irregular space data, that is so, with high dimensional parametric models, nonlinear models like Kepler had, that is such a difficult problem that statisticians can't just open up a book and say, hey, there it is on page 322. It's a very difficult problem. And we need statisticians such as Jesse Sajewski and others to work with us to try to do our best for these difficult problems. And I personally think Bayesian approaches is probably the only way of going. This is too difficult for standard, for simpler approaches. Okay, thank you very much. Yes, shuffling the data around, right. And the reason is, yes, the question is, when do you do permutation simulations and when do you do bootstrap simulations? Is that one way of asking your question? Okay, believe it or not, maybe we can get someone like Jesse to comment on this. It's a statistician's question more than mine. The issue is that the bootstrap is designed for independent variables. No, excuse me. It's designed for random variables, RVs. That's the theorems say, let X be an random variable. And time is not a random variable. It's a fixed variable. You can't go backwards in time. You go backwards in mass, but you can't go backwards in time. So when you plot mass versus eccentricity, then you can just bootstrap it. But it's not clear that bootstrap's the right approach for time series or for astronomical spectra or for imaging. Okay. Now, it's not that you can't do it. It's just that it's just not as clear. But if you shuffle the data, at least you've kept all your data points and you've kept all your observation points, and you do that 1,000 times, and you haven't doubled up on anything, and it might be wiser. I personally don't know whether it's wiser to do a bootstrap or a permutation on a time series, on an irregular space-time series. I don't know. Yes. Yes, shuffling will break down all periodicities, so it is sort of like a null test. It's testing a null hypothesis.
And the null test is great, as long as you are also trying to preserve something about the statistics.
It maintains the noise structure, which can be very odd and very difficult. It could have outliers, it could be non-Gaussian, it could be anything. Right. So I actually think this is definitely, everyone should be doing permutation or bootstrap tests. It's so easy. And it really helps a lot. My problem is that they're not also checking the autocorrelated behaviors that can mimic periodicities, particularly with irregular spaced observations. Okay, let me show you this. This is not a trivial point. You can't, so many times astronomers in the past, 1980s and 70s, all are hooked up about this in variable star research. There. Do you see how the Gaussian process of regression completely blew up during the 6 months when there was no data? That's the problem. The problem is that even if you put in a sine wave in here, as soon as you get to these irregular spacings, it can blow up and can give you completely wrong signals, completely wrong. If it's autocorrelated, if it's random white noise, you don't get that as much, but if it's autocorrelated. So you got to watch out for that, and that is the test that most astronomers are not doing, in my opinion. Yes? Yeah, look, I'm sympathetic. Yeah. I'm quite sympathetic. I actually agree with you. And is Eric Ford in the room? Eric, I hope that you tomorrow can mention the SAMC workshop that's going to occur starting in a few weeks for many months. And in this SAMC workshop, I hope that one of the topics will be to engage prominent statisticians, really smart, knowledgeable statisticians, to work harder, as you asked, to try to get us methods that allow us to have unevenly spaced observations, but still get some of the power out of some of the traditional methods like autoregressive analyses and things like this. So, Thank you, Eric. He wants a reproducible algorithm, but not necessarily evenly spaced. Thank you.
Ever seen the weather at a telescope?
Well, why don't you guys spend a little bit of money and put your telescopes in outer space? Yes, you do. In fact, that's Kepler and TESS and others as well, of course. Yes, sir.
I guess this is related to the last question. I'm just curious if there's any continuous time generalizations of ARMA type models.
Excellent. And that I'm sorry, I had only one lecture to give, and I completely agree with you. I think from ARMA, it goes to karma, okay? Not the karma like Indian philosophy, karma with a C for continuous. And that's right, one makes additional assumptions about the smoothness, certain characteristics about the smooth behavior, and that allows you to extrapolate between them. This has been used by a brilliant astrostatistician named Brandon Kelly and his colleagues for quasar variability from wide field optical surveys designed for supernova searches and quasar searches. And in my opinion, and he found karma really works beautifully for finding quasars, and in my opinion, karma can work very well for stars as well. In fact, I think this is the way to go. Thank you.
Transit, how can you deal with that?
Well, our colleague Suzanne Aigrin has a distinguished lecture at the IAU last year where she said precisely this. We need methods that can pull apart the signals of the star and the signals of the planet, but when they're the same characteristics, this will be impossible. So insofar as they become very close, then it becomes impossible. It's just impossible. We can't even hope to do it. It's not magic. Okay. But insofar as they are different, then there are techniques. I haven't mentioned another one called independent component analysis, ICA, which is a non-parametric way, not a parametric ARMA model, but a non-parametric way of pulling apart very different signals, and it's used. Well, the original paper in ANA a few years ago by Waldman has a wonderful title on exoplanets and cocktail parties. And if you don't understand that title, let's have a drink. Okay, it's a great title. I love the title. Okay, thank you.
Let's thank Eric. And let's thank all of our speakers and Deborah for chairing this morning too, please. Okay, did everybody get their banquet tickets? Who wanted to get banquet tickets? Yes, no, maybe, okay. All right, if you haven't done it, do it now. If you're having trouble doing it, talk to Ellen, because we can help you. If these are yours, come get them as you're walking out. I'm going to put them down over here. They were left at the registration table. I think that's it. We have a great evening. We will see you back here at 8:30 tomorrow morning. And thank you. And if you haven't signed up for a subgroup, go ahead and do that too on your way out. So thanks, everybody.